So in this video, we're going to look at the proof that root 2 is irrational. Okay, so I'm trying to prove that root 2 is actually irrational, and I'm using proof by contradiction. So if this is my statement P, that says that root 2 is irrational, by using proof of contradiction, I'm first going to assume that not P, that in this case not P is true. Now, by saying not P is true, it tells you that root 2 must be a rational number. So root 2 is a rational number. Now, what is a rational number? A rational number is a number where you can have root 2 can be rewritten as a ratio of two numbers, or two integers in this case. So let's have these two integers a and b, such that a is a integer and b is a integer, and yes, b should not be equal to 0, but also that a and b must have no common factors, must have no common factors. Okay, so this is what I'm assuming. So well, I'm not assuming this thing. What I'm assuming is not P is true, but because not P is true implies that root 2 must be a rational number. This is what's coming from the definition of rational number. This is something that I know must be true for all rational numbers. Okay, so which also tells you that if I start looking, if I look at this root 2 as a rational number, then if I square both the sides, that will be 2 equals to a square over b square, and what I have over here is 2b square equals to a square. Now from here, from the second piece over here, I can conclude that a square is an even number. Why is that? Because a square has been written as 2 times some integer. B is some integer over here, right? I've already claimed that b is an integer, b square is an integer times 2 is also an integer, which happens to be an even integer, and a square happens to be an even integer here. Okay, if a square happens to be an even integer, then what does that imply about a? Well, if you look at my last video, we just proved a theorem where if a square is an even number, it also implies that a is even. So again, look at one of my last videos where I've looked at the theorem of proving that if a square is an even number, that also implies a is even. But if a is even, then a can be written as 2 times some integer where k is an integer, because every even number can be written as 2 times some integer. So if a can be written as 2k, let's take this concept of a here, which is 2k, and plug it in this box here. Okay, so that tells you this is going to be 2b square equals to a square, and a square is here 2k square. So that gives you 2b square equals to 4k square, which gives you b square equals to 2k square. Okay, so if b square equals to 2 times k square and k is some integer, then I know that b square is an even integer. Okay, this is an even integer. So if b square is an even integer, from my theorem that I used over here for a, it also tells you that b is an even integer. And if b is an even integer, okay, coming back to this piece over here, coming back to this box here, if a is an even integer and b is an even integer, that does tell you that there is a common factor between a and b, which happens to be 2. Because a is an even integer, b is an even integer, I can take out 2 from a and b, which means there's a contradiction of this piece over here. The contradiction where I claim that a and b must have no common factors, but by assuming not p is true, I was able to conclude that there is a common factor between a and b, which happens to be the number 2. And because it happens to be number 2, then my claim here is that not p over here, which I originally started with the assumption that actually being true, must be false. So this actually is false. So let me just kind of do this nicely over here. So not p must be false, which implies that P, the statement P, must be true. Okay, so if P is true and P is a statement over here, which tells you that root 2 is an irrational